Welcome to the course on audio signal processing for music applications. This week we're talking about the harmonic model, and in this programming lecture I want to talk about the implementation of it, in particular the first part of it, the part that requires detecting the fundamental frequency so that we can then identify the harmonics of a given sound. So we will be talking about one particular algorithm, the two-way mismatch algorithm. That's an algorithm that we presented in the theory lecture, and it's a frequency domain algorithm that basically tries to identify harmonic series, possible harmonic series that match the peaks of a spectrum. So in this plot, we see the measured peaks that we have identified, and then we keep trying different predicted fundamental frequencies and the harmonics of it, and we measure the error, we measure the distance between these two lists of values. And we do that by measuring two errors, the predicted to measure, so the difference between the distance between the predicted and the measured values, and also we have another measure which is the measured to predicted error. But let's go directly to the actual code. Okay, in the SMS tools package, in the util functions file, there is the code for the two-way mismatch algorithm. The core of it is a function called two-way mismatch. In fact, there is a C version and a Python version. Now we will go through the Python version. When we run it, we normally use the C version because it's more efficient. So this algorithm, what it does is it receives the peaks, the frequencies and magnitudes of the peaks. It receives a list of candidates, of frequencies of candidates of fundamental frequency, and it basically identifies which is the candidate that has the smallest error. So it does that by measuring the two errors, the error predicted to measure, which is this part, and then the measure to predicted, which is this part. Within it, it keeps identifying all the distances between all the values of the harmonic series and the peaks, and it has different ways of comparing those. We're not going to go into detail of that, but of course, feel free to go into it. And then finally, it just creates an error array, which is the list of errors of all the candidates. Okay, so we have in the error, we have all the errors for every single one of the candidates. And then what we do is we choose the minimum of those errors, and the fundamental frequency is going to be that candidate that has the minimum error. And then this function is wrapped by another one that is the one responsible for generating the candidates and calling the function. So this F0 to WM receives again the peaks of the spectrum, and then it receives the control parameters. So like the maximum error allowed, this is the error that will be allowed for the fundamental frequency to be accepted as such. And then the range of the fundamental frequency, so from minimum and maximum F0. And then there is one value which is kind of a memory, a tracking value, that is basically the fundamental frequency of the previous frame. And this will allow us to refine the fundamental frequency by restricting that the fundamental frequency should be as smooth as possible. But the algorithm here is very simple. In fact, it just takes the list of peaks that are within the minimum and maximum value of the frequencies. And the rest, it just makes a few more comparisons about that. There is a lot of room for improvement in this algorithm, in the sense of generating more candidates so that we do a more exhaustive trial of different frequencies. But for efficiency reasons, we made this simple implementation so that allows us to compute this quite efficiently. Okay, so I wrote a little script that basically does an analysis of a single spectrum, and then it computes the errors of all candidates. Okay, so in here I have this little script that from a sound, the sawtooth sound, it just computes one DFT. So here is it computes one DFT of that particular sound. It finds the peaks, it finds it interpolates the peaks, and then it generates possible candidates of the fundamental frequency in a similar way than what we just saw, but even more simply, in the sense that we are taking the candidates as all the peaks that lie within the ranges that we specified. And then it calls the two-way mismatch algorithm, but I modified the function, so I have it here in a way that instead of returning just one value, the fundamental frequency that is the minimum error, it returns all the errors. So it returns the array of all the errors for all the candidates, so that we can look at them and see how they behave. Okay, and then it prints. Here it just prints the spectrum and the peak, so we can understand a little bit what's going on. Okay, so let's run this. So let's run a test. Okay, and this is the spectrum, the magnitude spectrum, and the peaks that we found. So let's maybe zoom in a little bit so that we can see a little bit what is going on. Okay, so these are clearly the harmonics of the sound. It has also found peaks like before the fundamental frequency and one after the fundamental frequency, but that's well, basically it has identified just the harmonics. So now let's plot and let's print some of the intermediate values of all these. Okay, so clearly the first thing is the candidate. So if we print the F0C, this is the candidate, and it's going to be the peaks that lie within the frequency range that we specified, which was between 50 and 2000 hertz. So the candidates are the first 5 peaks, and if we print their frequencies, so by doing ipfreq and F0 candidates, those are the frequencies that lie within the frequency range and that we're going to test in the algorithm. So we're going to test 166 hertz, 440, 637, etc., etc. So now let's print the errors that it returned. So F0 errors, which is the output of this algorithm, will have the errors for every one of these values. So for 166, we have an error of 4.8. For 440 has minus 0.13. So clearly this is the smallest of all errors, and this is indeed the fundamental frequency, the candidate that is the best one for as a fundamental frequency. So these error values are a little bit misleading because they are not bounded within a particular range. It can be even be negative, like in this case. But clearly, the larger the error, the less chance is that it's going to be a fundamental frequency. So we will be focusing on the lowest errors that we have. Okay, so this works quite well. Now we can go into another file that basically does this for the whole sound. So we will be iterating for the whole sound. We are just doing the exact same thing. We're taking the sawtooth sound and we are trying a different window. We keep see if we can get a different type of result, and we take the FFT. We define the minimum maximum, and we call a function F0 detection, which in fact is on the harmonic model file. In the harmonic model file, there is this function called F0 detection that does all what we talked about. Basically, it accepting gives from the input sound, the sampling rate, window, FFT size, and the values given by the user. It iterates over the whole sound, and it calls the DFT, the peak detection, peak interpolation, the two-way mismatch algorithm, and then it decides which one would be the best fundamental frequency. There is a few sort of constraints to make sure that the fundamental is stable in time related with this track that we talk about. So, but basically it returns just the fundamental frequency that it considers to be the best. Okay, so let's now look at test 1 and let's run it. So let's run test 1. Okay, and now in fact we can just show the F0. Okay, so this is the values that it has returned. Well, the hop size that I specified was quite large, 1,000, so it is not that many samples, so that's easier to look at. And okay, clearly there is not a perfect fundamental frequency identified. It kind of varies, like it goes from 439.9 to 440 something. So in fact, if we plot this array, we will see the variation that we will have here. Okay, well, let's maybe get rid of this, and let's get rid of this, and now let's plot it again. Okay, now we can zoom in to the very top. Okay, so clearly it moves around 440, and these variations are caused by clearly by the errors of the peak detection algorithm and the interpolation, so that we are not really exactly at 440. But of course the error is very small, it's less than 1 hertz error. So this is 440 and 440.5 and a little bit below. So this is clearly a quite small deviation from the nominal value that is 440. If we change these values, we might get better results. So for example, instead of having the window being 1001, let's make it twice as much, and the FFT size, let's make it twice as much. Okay, and no, times 2. Okay, and now we will, so let's see that before we were 439.95, 440 point something. Let's see if it does any difference by looking now at these values. Okay, so this is what we got now, and it's a little bit better. So we can see the difference between these two values. Now the error is smaller than before. In fact, if we plot now this F0, well, there is this exponential to the minus to the minus 2. So clearly this is a very small, it's a smaller error range than what we had before. So the slowest now is 439.9, and the highest value is 440.042. So that means that as the window gets larger and the FFT gets larger, the zero padding increases, we will have better values. Okay, now let's look at the real sound, and let's finish by running it on this oboe sound. And basically I do exactly the same thing. So I can just run this test 2. Okay, this will compute the fundamental frequency of this oboe sound, and now if I plot this F0, okay, and now we will have to zoom into the meaningful range. Okay, and well, there is definitely also a variation, but here there is both the variation that may be caused by errors and the variation that is clearly natural to the playing of the oboe sound. So for example, this sound is clearly higher than 440, so the oboe sound was played a little bit higher in frequency than 440, so around, in fact, 442. And there is kind of a periodic oscillation that makes sense to be present in the sound. And of course, there might be some of these oscillations that may be caused by some error. But this is a very interesting way to try to understand what is going on, and both in terms of the algorithm and in terms of the sound, in terms of this oboe sound and the natural oscillations that might be caused by either the acoustics or the performer that is playing this note. Okay, and that's all I wanted to say. So basically, we have talked about an implementation of the two-way mismatch algorithm, and I think that has given us a view on the issues of how to detect the fundamental frequency. Of course, we have used Python and a number of these packages and the implementations that we have in the SMS Tools package. So that's all. So this was the first programming class on this harmonic model week. And then on the next lecture, we will then add the whole model and include this fundamental frequency into a harmonic analysis. And we will be able to do both the analysis and synthesis of sounds. So thank you very much, and I see you next lecture.